Okay, hello everyone in a new video. So we have reached part 3 of chapter 9, which is the chapter of equilibrium of a body, and the third unit of mechanics. Then we have reached exercise number 7, section 9. We have a spring R of free length L0 given by 0.2 meters. And of stiffness K is equal to 100 newtons per meter. So here the stiffness of the spring is given by 100 newtons per meter, which means in order to elongate or compress the spring by 1 meter, we need to exert a force worth of 100 newtons. So indeed K reflects the stiffness of the spring, so how much the spring is stiff or strong. We fix the extremity O of R to a support and we suspend to its free extremity a ball of mass m is equal to 0.6 kilograms. Then the moment we know the value of a G, we can determine the magnitude of the weight. And of center of gravity G, see document 1. So they mentioned this document, now we can use it. Now notice that till this moment they didn't mention anything about the condition of equilibrium. So, or let me say the following. Yet we didn't mention the forces. Number 1, they are telling us the two forces exerted on the ball are its weight W and the tension T of the spring. So till this moment they didn't mention anything about the condition of equilibrium, then we are not allowed to use it. In 1.1 they are telling us to specify whether each of the two forces is a contact force or an action at a distance. We know that the only three forces that act at a distance are given by the weight, the electric, the magnetic. So in this case the weight is classified as an action at a distance. And all other forces are classified as contact forces, and in particular the tension T with no exception. Then the tension T is given by contact force. Now in 1.2 they are telling us calculate the value of W, take G is equal to 10 newtons per kilogram. This reflects the fact that this experiment is being performed on the surface of the earth. Then what does 10 newtons per kilogram means? That each kilogram is being acted by 10 newtons. Now we need to calculate the value of the weight, and by the value it means the magnitude. We know that the magnitude of the weight, since we know the mass and we know the value of G, is given by W is equal to M multiplied by G. And the value of the mass is given by 0.6, and the value of G is given by 10. Then plugging this on the calculator, the value of W is given by 6. Since both M and G are expressed in SI, so the value of W will be expressed in SI, which is newtons. Then the weight is given by 60 newtons. Now in 1.3 they are telling us to state the other characteristics of W. And we know that the characteristics are given by the point of application, the line of action, the direction, and the magnitude. And here other refers to the point of application, the line of action, and the direction, because already on 1.2 we have discussed the magnitude. Then we need to list them in the Pilgrim order, so let's start by the point of application. And because W is being classified as an action at a distance, then the point of application will be the center of gravity G. And we know that always the weight acts vertically downward. So the line of action is vertical and the direction is downward. So this is it for number 1. Now in number 2, they are telling us for a length L is given by 0.25 meters. Then notice that here they gave me the initial length, and here we have this length. So this length corresponds to the final length. So now we have that L is equal to 0.25 meters. Knowing the initial length and knowing the final length, one, for example, can calculate delta L, because delta L can be calculated using two methods, either using Hooke's law or from its definition, which is given by delta L, final length minus initial length. Now in 2.1 they are telling me calculate by applying Hooke's law the value of the tension T. Then here we are interested in determining the value of the tension. Now suppose that we ignore this statement and without referring to Hooke's law. So what are the different methods to calculate the value of T, either by Hooke's law or by the condition of equilibrium? But notice that till this part they didn't mention anything about the condition of equilibrium. So we cannot use the condition of equilibrium to determine the value of T. For this reason, as a hint, they are telling us by applying Hooke's law. So let's say as a title, apply Hooke's law. And Hooke's law is given by T is equal to K multiplied by the elongation. Here the elongation is not denoted by delta L or X, so we are free to choose either. Then I will choose delta L. No need to construct a triangle for this formula because this is the quantity that we want to calculate. Now in order to determine T, we need to know K, which is given, and delta L can be calculated using this. So let me say that delta L is equal to the final length minus the initial length, which is given by 0.25 minus 0.2, which is equal to 0.05. Since this is expressed in meters and this is in meters, then the difference will have the same unit, which is meters. Then this is equal to the stiffness, which is given by 100 multiplied by delta L, which is given by 0.05. Plugging this on the calculator, then the value of the tension is given by 5. Since both are expressed in the SI, so the value of T will be in the SI, which is in newtons. Then the value of the tension is equal to 5 newtons. Now in 2.2 they are telling us to state the other characteristics of the tension. And other here refer to the point of application. To the line of action. And the direction. And we always list them in this order, which is the Pilden. Now because the tension is classified as a contact force, then the point of application will be the point of contact between the two bodies that are at interaction, which is given by the point of contact A. As for the line of action, we know that always the tension is along the string. And in this case, along the string is given by vertical. As for the direction, it's opposing the weight, which means it is downward. Now as for 2.3, and by represent it means that we need to draw. Then in order to draw the forces W and T, we need to have the length of these forces. We know their magnitudes because the magnitude of the weight is given by 60 newtons, whereas the tension is equal to 5 newtons. And to determine the length, this is done by the connection, which is the scale, knowing that each 1 centimeter corresponds to 2 newtons. What about so this is the connection. First let's determine the length of the weight. So 60 newtons what is the length of the weight? Then now we can crisscross. 6 multiplied by 1 divided by 2, this is equal to 3 centimeters. Now as for the length of the tension, then each 1 centimeter also corresponds to 2 newtons. What about 5 newtons? Then 1 multiplied by 5 divided by 2, this is equal to 2.5 centimeters. Now let's represent these vectors. So let me draw the solid S, or the object. They are not naming it to be the solid. Now the spring is not much important, but what is important to represent the points G and the points A. So the weight vector will be represented from the point G vertically downward, and the length of this vector is 3 centimeters, corresponding to 60 newtons according to the scale, and the name of the vector is W. So recall that these, just to indicate, they are not important, just to indicate that each one is given by 1 centimeter. Now as for the tension, it will be represented from the point A vertically upward like this. So the length of this vector is 2.5 centimeters, worth 5 newtons, and the name of this vector is the tension T. Now in number 3, they are telling us the ball is still connected to the spring, is now in equilibrium. So here, let me fix this. This is 2.4. Now in 2.4, they are telling us the ball is not at equilibrium Y. So in order for the ball to be at equilibrium, we need to refer to the properties of the forces, and we need to check that if both of them have the same line of action. So they have the same line of action. They have opposite directions because T is up, W is down, whereas the magnitude is not the same. One of them is 5 and the other is 6, because the magnitudes are not the same, which means that the ball is not at equilibrium. So let me say, since W and T are not equal in magnitude, and this is because 5 newtons is different than 6 newtons, then the ball is not at equilibrium. Now as for number 3, they are telling us the ball still connected to the spring is now in equilibrium. Now because it is at equilibrium, we can use the condition of equilibrium determined with the justification the value of T. So because we are interested in equilibrium, let me write here as a title at equilibrium. And on the left hand side of this equation, we write the different forces acting on the solid given by the weight and the tension. And on the other side of this equation, we write a zero vector corresponding for the condition of equilibrium. So the first member of this equation tells us that the effect of the forces acting on the solid cancel each other, whereas the second member correspond for the condition of equilibrium. Now dragging T to the right hand side, we will write that W is equal to minus T. And since we are interested in the value, so let me write in magnitude that W is equal to T. But here notice that we are interested in determining the value of T using the condition of equilibrium. Now the weight will remain the same, which is given by 60 newtons, and simply because we didn't change the mass and we didn't change the value of G. Okay, so W remains the same. Now in equilibrium, what will change is the value of the tension and not the weight. So let's say, but the value of the weight is equal to 60 newtons, then in this case the value of the tension is equal to 60 newtons. Okay, so here the moment it is in equilibrium, one of the values of the forces will change, either the weight or the tension, but in this case, because we didn't change the mass and we didn't change the value of G, so in this case the weight remains the same. As for the tension, it will change and it will become equal to the weight. And now let's move to the next exercise. Exercise number 8. Section 10. The aim of this exercise is to verify experimentally the relation between the values of the gravitational field strength Gm on the moon's surface and the gravitational field strength G on Earth's surface. For this, we consider a spring R of stiffness K is equal to 50 newtons per meter. And a solid S of mass m. And we have that G is equal to 10 newtons per kilogram. Now this is G referred to the gravitational field strength on the Earth. Now first experiment. On the Earth's surface, we fix the extremity O of R to a support and we suspend the solid S to its free extremity A. At equilibrium, they mentioned the condition of equilibrium, so at any moment in this exercise we can use the condition of equilibrium. The elongation of the spring R is given by delta L1 is given by 12 centimeters. Then knowing that centimeter is not a unit of length, in order to convert from centimeters to meters, we divide by 100. And this is equal to 0.12 meters. Now S is submitted to two forces, then 1.1. Give the name of each force under which S is submitted to. So we know that because it has a mass, then it will be subjected to the weight W. And because we have a spring, then it will be submitted to the tension T. Now in 1.2 they are asking us to write the vector relation. And here the vector relation, it corresponds for the condition of equilibrium. And we can use it because it is already at equilibrium. So as a title we will write at equilibrium. Then on the left hand side of this equation we'll write the different forces acting on the solid as given by the weight and the tension. And on the right hand side of this equation we write the zero vector corresponding for the condition of equilibrium. Dragging T to the right hand side, then we'll have this equation. The first equation means that both forces acting on the solid S, their effect cancel each other, whereas the second equation means that both forces have the same line of action, opposite direction and same magnitude. Now in 1.3 they are telling us to determine the magnitude of each force. So the condition of equilibrium allows us to calculate the magnitude of one force when we know the other. So first we need to determine the magnitude of a force, and this can be done because we have K and we have delta L1, so using Hooke's law. So always in physics we need to mention the law that we are using. So apply Hooke's law. Then usually this statement they give it half a mark. So T is equal to K multiplied by the elongation, which is denoted by delta L1. No need to construct a triangle because this is the quantity that we want to calculate. Now the value of K is given by 50 and the value of delta L1 is given by 0.12. Plugging this on the calculator, then the value of the tension T. So let's denote this T by T1 since this carry the label 1. So 6, since both are expressed in the SI, so the value of T1 will be in the SI, which is in newtons. So T1 is equal to 60 newtons. And let's recall that what does the stiffness reflect? So 50 newtons per meter, which means that in order to compress or elongate the spring by 1 meter, we need to apply a force worth of 50 newtons. Now after we have determined the value of one of the forces, the magnitude, we can determine the other using the condition of equilibrium. So now because we know that W is equal to minus T, here let me say that we have T1, then in magnitude, then we drop down the vectors and each vector, and we remove the minus sign, so W is equal to the tension T1, but we know that the value of T1 is equal to 60 newtons, then in this case, W is equal to 60 newtons. Now in 1.4 they are asking us to deduce that M is equal to 0.6 kilograms, and by deduce it means we need to use the previous part. In the previous part, we have determined the value of the weight, and we are performing this experiment on the surface of the Earth, so we can use that G is equal to 10 newtons per kilograms. Then weight is equal to m multiplied by g, and we are interested in determining the value of m. Then constructing the triangle here, because we have multiplied, and w will be at the top, m and g at the bottom. Then m, which is denoted by capital M, is given by w over g. The value of w is given by 6, and the value of g is given by 10. Plugging this fraction on the calculator, then the value of m is given by 0.6. Everything is expressed in the SI, so the value of m will be kilograms. So the mass of this solid is given by 0.6 kilograms. Now in the second experiment, they are telling us the same experiment is performed on the moon's surface. Now, going from Earth to moon, one should keep in mind that the mass will not change, which is given by 0.6. As well as for the stiffness will remain the same. Then all other quantities are submitted to a changement, so they may change. Now the thing is that the same experiment also will be at equilibrium, but now the new elongation is given by delta L2 is equal to 2 centimeters. Knowing that centimeters is not a unit of length, in order to convert from centimeters to meters, we need to divide by 100. Then 2 divided by 100, this is equal to 0.02 meters. Now in 2.1, they are telling us determine the new magnitude of each of the two forces acting on us. So notice that this is exactly the same as this. So the same scenario that we have admitted here in order to determine both magnitudes, we will follow here. Then first, let's say apply Hooke's law. Which is given by T is equal to K delta L2. So always in physics we need to mention the law that we are using. This statement, they give it half a mark. And because this is labeled by the index 2, so this will carry the label 2. Now the stiffness K is given by 50, whereas delta L2 is given by 0.02. Plugging this on the calculator, then the value of T2 is given by 1. Since both K and delta L2 are expressed in the SI, so the value of T2 will be in the SI, which is in newtons. Then T2 is equal to 1 in newtons. Now recall that the condition of equilibrium allows us to determine the magnitude of one force in terms of the other. Then it is at equilibrium, so we can use directly that the weight is equal to the minus T2. Then in magnitude, then we drop down the vectors, and W is equal to T2, and we remove the minus sign, but we know that the value of T2 is equal to 1 in newtons. Then in this case, W, the new weight, is equal to 1 in newton. And here, because this weight represents the weight on the moon, so let me here write Wm. So this is the new weight on the moon. Now in number 2.2, they are telling us, knowing that the mass of S remains the same, deduce the value the value of Gm, and by deduce it means we need to use the previous part. In 2.1, we have determined the new weight, which is given by Wm. Then we can determine Gm knowing that the mass remains the same, because weight, mass, and gravity are related via the following formula. Then constructing the triangle. Here, because we have multiplied, and W will be at the top, M and G at the bottom. Putting our hand over G, then G, which is denoted by Gm, is equal to the weight on the moon divided by the mass. The weight on the moon is given by 1 divided by the mass, which is given by 0.6. This is equal approximately to 1.67. Since both weight and m are expressed in the SI, so the value of G will be in the SI, which is in newtons per kilogram. Then the gravitational field strength on the moon is given by 1.67 newtons per kilogram. Now, if you compare the values of a Gm and a Ge, or a G on Earth, what do we notice? We notice that each kilogram on Earth is being acted by 10 newtons, whereas each kilogram on the moon is being acted by 1.67. This reflects the fact that gravity on Earth is much stronger than that of the moon. Now let's determine by how much. In 2.3 they are asking us to verify the following relation. And since this relation to be verified, then we don't know if this relation is true. Now the value of a Gm is given by 1.67 as calculated here. We need to check whether it is equal to 1 over 6 multiplied by 10, because we know that the value of a G is given by 10. Here the question mark reflects the fact that we are verifying this equation. So whenever we need to verify an equation, the equality must have a question mark. So now 1.67, is it equal to this expression, which is given by 10 over 6? Now plugging this expression on the calculator, I repeat, now plugging this expression on the calculator, one can verify that 10 over 6 using the calculator is given by 1.67, so indeed it is verified. So in this case, Gm, so here verified, it's important here to write verified. Sometimes they give it half a mark. Then Gm is equal to 1 over 6 G. Okay, so what does this mean? If we cross multiply, for example, just to extract the physical significance from this equation, we have that G is equal to 6 Gm, which means that the gravitational field strength on Earth is 6 times stronger than the gravitational field strength on the moon. And now let's move to the following section, which is section number 11. And the title of this section is Characteristic Elongation Tension Curve of K. Now here the case that we are discussing is the case of elongation, but we know that the spring can undergo two modes that are given by either the elongation or the compression. So in the case of the compression, simply the title of this curve will be, or the title of this section will be, Compression Tension Curve. Now we are familiar with such type of curves that we have faced or encountered for an ohmic conductor, or in the case where we are discussing the following relation: weight is equal to m multiplied by G. Now the title of this curve will be the variation of t as function of delta L, and this curve gives the explicitly all the graphical relation between t and delta L. So whenever we know t, we know delta L, and vice versa, for example. So then this is one of the important things that we can extract from such type of curves. Then in reality there are 6 important things to notice. And let me start by idea number 1 is the shape of the curve, because the shape of the curve is important for us. And in this case, the shape of the curve is a straight line passing through the origin. Then let me say the characteristic Then why we are naming it to be elongation tension curve? Because the x-axis is labeled by the elongation, as for the y-axis is labeled by the tension. Then the characteristic elongation tension curve of which quantity? Of the stiffness K. So recall that K is a physical quantity, which is the stiffness. Is a straight line passing through the origin. Now, as for idea number 2, we know that whenever the shape is a straight line passing through the origin, or it is a straight line, then we can determine the slope. The slope represents a physical quantity. In this case, the slope represents the stiffness K of the spring. Then let me say the stiffness K of the spring is equal to the slope of the characteristic elongation tension curve. Then recall in the case of resistor, we used to say the resistance of the resistor R is equal to the slope of the characteristic current voltage curve, because this was labeled by the current, this was labeled by the voltage. So in this case, this is exactly the same, but we are replacing current by elongation, tension by voltage. Now, as for idea number 3, we know that graphically we can extract the value of delta L knowing T and vice versa. Then let me say graphically if the tension is 2 newtons, then the elongation is 4 centimeters. So how come? Then if you know the value of T to be newtons, here we are using the graph, so usually this we give it half a mark. If you know that the value of T is given by 2 newtons, then corresponding to the curve, it represents this point on the curve. Going on the x-axis, we have that delta L is equal to 4 centimeters. Vice versa, we know that graphically if the elongation is 6 centimeters, for example, then 6 centimeters corresponding for this point on the curve, having the value of 3 newtons, then the tension is 6 newtons. Now, idea number 5. Now notice here something, that the curve stops at this point. This point represents the point where the spring loses its elasticity or breakdown. Then let me say graphically so this point is characterized by two values. So the maximum tension in this case is given by 3 newtons. So if any applied force to the spring is greater than 3 newtons, then the spring may break out, may loses elasticity or break out. Then let me say graphically, the maximum tension under which the spring loses its elasticity is T max is equal to 3 newtons. Then I repeat, usually such type of curves that represents the variation of T as function of delta L, they stop and are limited at some point. This point is the point of under which the spring loses its elasticity, is being represented by two values. So the value corresponding for the y-axis, which is T, this represents the maximum tension. So any applied force to the spring greater than 3 newtons, then the spring may break out or loses elasticity. So the same here. Now any elongation undergone by the spring greater than 6 centimeters, then in this case the spring also may break out or loses its elasticity. Now we can say graphically the maximum elongation under which the spring loses its elasticity is delta L max given by 6 centimeters. Then these are the 6 important things to notice in an elongation tension curve. Then we have 2 additional ideas corresponding to the limiting point under which we have a value of T max and a value of delta L max under which the spring loses its elasticity. Now we need to discuss again the method of the slope that allows us to determine the value of K. Let me drag this document downward like this, and let me say that or pose the following question, which is given by how to determine the slope. Then now we are familiar with such methods. The first thing that we do is to write the definition that relates the physical quantity K, which is the stiffness, with the quantities T and delta L. Then let me say step 1, write the definition. Which is given by the stiffness K of the spring is equal to the slope of the characteristic elongation tension curve. Now step number 2 is to choose any 2 points belonging to the curve independent of the positions of the points. Then step number 2 is to choose any 2 points on the curve then my choice will be, for example, say the point A and the point B. Then now let's write the coordinates of the points A and B. Then let me say that A is given by, we always start by the elongation, then the tension, then 2 centimeters with 1 Newton. As for the point B, it's given by 4 centimeters and 2 newtons. Now step number 3 is to convert to the SI. Then we know that the SI unit of centimeters is the SI unit of length is meters and not centimeters. In order to convert from centimeters to meters, we divide by 100. Then the coordinates of the point A are given by 0.02 meters, 1 newtons. As for the point B, it's given by 0.04 meters and 2 newtons. Now step number 4 is to calculate the stiffness K using the following formula. Which is given by K is equal tension at the point A minus tension at the point B over the elongation delta L at the point A minus the elongation L delta L at the point B. Now let's calculate it. Then K is equal to TA minus TB over delta LA minus delta LB. Then the tension at the point A is given by 1. The tension at the point B is given by 2. Divided by delta LA, then we choose the SI, which is given by 0.02, minus delta L at the point B, which is given by 0.04. Now here, when calculating the following fraction, you need to take into consideration that you need to calculate the numerator and the denominator separately. Then so here, for example, you have minus 1 over minus 0.02, so minus will cancel out with minus, and this answer will be given by 50. Or simply you plug this expression on the calculator and the value of K will be given by 50. Since here we made sure that the values of A and B are given in the SI, so the value will be in the SI, which is in newtons per meter. Then K is given by 50 newtons per meter using the slope method. And now let's move to the next section, which is related to converting units, section number 12. And first, let me state the following note. To convert so let me say, okay, first let me say the following. We know that in order to convert from centimeters to meters, we divide by 100. Sometimes you are interested in converting from newtons per centimeters to newtons per meter. Now from centimeters to meters we divide by 100, but here notice that the centimeters is in the denominator and not in the numerator. For this reason, in case we are converting from newtons per centimeter to newtons per meter, which is the SI, this is extremely important, we multiply by 100. Because why we are doing so? Because here we are using mixed dimensions, mixed units, and whenever it comes to mixed units, the thing is a bit tricky. Now all other units can be converted using this line or this scale. For example, we know that in order to convert from centimeters to meters, we divide by 100. Now using this one, the empty spaces may be labeled by meters. So here if we put m, and if you are interested from converting from centimeters to meters, we are moving to the left, then we divide by, then 1, 2, so we divide by 100. Okay, so for this reason, from centimeters to meters, we divide by 100. Now if you are interested in converting from grams to kilograms, so this is grams, then from grams to kilograms we are moving to the left by 1000, then from grams to kilograms we divide by 1000. And more importantly, the note that I have mentioned here is that converting from newtons per centimeters to newtons per meter, we multiply by 100, which is different than this one. Now exercise number 9, section 13. A spring balance is suspended vertically with its upper end fixed to a support. Its lower end carries a solid S. The spring balance undergoes a compression as shown in document 1. Previously, all the exercises that we have discussed are in the case of elongation, but why this is compression? So notice that here the solid S is connected to the following solid, which is in bold. Now this solid is compressing the spring, so as the solid S goes downward, the spring inside this tube will be compressed. Now the curve in document 2 shows the variation of the magnitude of the tension T exerted by the spring on S as a function of the compression X of the spring. So this curve shows the variation of T as function of X, and the shape of this curve is straight line passing through the origin, reflecting Hooke's law. Now we know that the value of G is equal to 10 newtons per kilogram, which reflects the fact that this experiment is being performed on the surface of Earth. Now number 1, they are asking us to complete the following table. So it consists of 4 columns. Now, when the tension is given by 1 newtons, so what does this curve function as, or what's the benefit from this curve? If we know the value of T, we can determine the value of X, and if we know the value of X, we can determine the value of T, in which this curve represents the passage from T to X. So when T is equal to 1 newtons, it corresponds on this point on the curve, which has the value of 1 centimeters. If X is equal to 3 centimeters, it corresponds for this point on the curve, having the value of T3 newtons. And if T is 5 newtons, it corresponds to this point on the curve, having the value of 5 centimeters. Then the values are given by, the missing values are 1, 3, and 5. And we have done this graphically. Now in number 2, they are telling us Hooke's law is given by the relation T is equal to Kx, where K is a physical quantity that characterizes the spring. Give the name of K. Now K is said to be the stiffness of the spring. This is the name of K. Now in number 3, they are telling us to calculate its value in the SI unit. And the value of K is determined using Hooke's law. Then apply Hooke's law. Hooke's law is given by T is equal to K multiplied by X, and we are interested in determining the value of X. Then constructing the triangle of this formula, T at the top, K at X at the bottom. Putting our hand over K, then K is equal to T over X. Now which T and X we should use, corresponding for the same point or for the same column. For example, we can use this one. When the tension is equal to 3 newtons, X is equal to 3 centimeters. But knowing that centimeters is not the SI unit of length, in order to convert from centimeters to meters, we need to divide by 100. So this is equal to 3 divided by 0.03, which is equal to 100. Since both T and X are expressed in the SI, so the value of K will be in the SI, which is in newtons per meter. Then the value of the stiffness of the spring is given by 100 newtons per meter, which means that in order to elongate or compress the spring by 1 meter, we need to apply a force worth of 100 newtons. Now in number 4, they are telling us as submitted to two forces, T is one of them, name the other force. Then for sure, because the solid has a mass, it will be subjected to the weight. Then the other force is the weight W. Now in number 5, S is at equilibrium, then at any moment we can use the condition of equilibrium. The maximum compression of the spring is given by X is equal to 6 centimeters. Then in 5.1 they are asking us to write the condition of equilibrium. Then as a title we will write at equilibrium. And on the left hand side of this equation we write the different forces acting on the solid given by the weight and the tension. And on the right hand side of this equation we write the zero vector corresponding for the condition of equilibrium. Dragging T to the right hand side, it will gain a minus sign. Now this is it, no need to extract the magnitude property. Now in 5.2 they are telling us give graphically the magnitude of the corresponding tension. So here the corresponding tension, they are talking corresponding for X. And because we need to use the graph, so we need to mention it graphically. Usually they give it half a mark. Now we know that the maximum compression is given by 6 centimeters. Here no need to convert it to meters because already the x-axis is labeled by centimeters. Then we have 6 centimeters correspond for this point on the curve, having the value of T is equal to 60 newtons. Then the corresponding maximum tension is given by 60 newtons. Now 5.3 they are telling us deduce the maximum magnitude of the weight that can be measured by the spring balance. Now because we have determined the maximum tension, the maximum weight can be deduced from the condition of equilibrium because we have that the weight is equal to the minus the tension. So in magnitude, now we drop down the vectors and we remove the minus sign. Then W is equal to T, but we know that the maximum tension, let me say here that T max is equal to 60 newtons. Then in this case, the maximum weight is given by 60 newtons. Now in 5.4 we need to calculate the maximum value of the mass that can be measured. Knowing the maximum weight and knowing the value of G, we can determine the value of the maximum mass because weight is equal to M multiplied by G. So if this is the maximum, then this is the maximum. Then W max, which is given by 6 over G, this is equal to 0.6 kilograms. Then the maximum mass is equal to 0.6 kilograms. Now in number 6, they are telling us a greengrocer cannot use the spring balance to measure 1 kilogram of potato bag. Justify. And this is simply because the mass of this bag is greater than the maximum mass to be measured. So since the applied mass is greater than the maximum mass, that the spring balance can measure, and this is because 1 kilograms greater than 0.6 kilogram, then the greengrocer. So we are just rephrasing this statement, cannot use this spring balance. Or let me say, then the greengrocer cannot measure the mass of this bag. Cannot use, let me rewrite it, it's okay. Cannot use this spring balance to measure this bag. So that's it for me in this video, guys. In part 4, we'll complete solving exercises on this chapter.